All right, welcome everybody to the SESE Colloquium. I'm Ed Garnero, if you don't know me. I'm a faculty in geophysics. And I'm super excited to welcome Sam Hansen here to speak from the University of Alabama. Sam got her middle school degree in upper state. No, serious. No, she got her bachelor's at the University of Wisconsin and her master's at the University of Wisconsin, geological sciences, some engineering something with your bachelor's, and went on to get her PhD at Penn State.
Penn State. I worked at Santa Cruz, darling.
No, that's your postdoc.
Yes.
That's right. Oh my gosh. And I know better because I met Sam when she was finishing her PhD at UC Santa Cruz, and I was there on sabbatical. Sam went on to Penn State for a postdoc, and then from there you went on to University of Alabama. She's been there like 14-ish years. She's a full professor there. Sam's got a long list of distinctions: Fulbright Scholarship, Kavli Fellow from the National Academy of Sciences, a University of Alabama Presidential Faculty Award, and a Presidential Early Career Award, a PCASE, and you got to shake a president's hand. Very exciting. And 6 field seasons to Antarctica. I assume we're going to hear something about those. So she's super embedded in service roles, chair of boards. Right now, you're in the EarthScope board, chair, almost president, something big, lofty.
Sure, yeah, sounds great.
And she's a tireless, like researcher. It's really great. I've had the great fortune to work with Sam, and like things get done working with Sam. So I'm going to shut up, and will you welcome Sam Hansen with me?
I promise Ed and I know each other better than he makes out. Well, thanks for having me here today. It's been a lot. I was here Sunday, I came in, and so I've had a few days to meet people, and it's been a lot of fun. So today I'm going to talk about some various projects I've been doing in Antarctica over the last 15-ish years, a little more, just to kind of give you an outline of where this talk is heading. I realize not everybody in here is maybe that familiar with Antarctica. So I'm going to start with just a little introduction to the continent and kind of what it's like to work there. And then I'm going to talk about 3 different projects. I'll highlight these to show you what we're doing with the data we're collecting there, and kind of why this is important. And then I'll wrap it up with a few summary comments. But just because I don't want to forget, I'm going to put my acknowledgements right up front. There are a lot of people that have contributed to the work you're going to see today. The polar field teams that made all this data available, there's way too many to list. A lot of the work that you see is related to things that some of my prior graduate students have done. So Coyote, Greg, Jordan, and Lindsay were all students with me. I have collaborators at different locations, including Erica Emery, who's at Sandia National Lab, Sebastian Rost at the University of Leeds, and here at ASU, I'm working with Ed, Mingming Li, and Dan Shim. The EarthScope Consortium provides a lot of support for this. They're the ones that help give us our instrumentation and to archive our data. And of course, the National Science Foundation for funding. So when I'm giving a talk to a general audience about Antarctica, I kind of like to start with this slide just to kind of get everybody on the same page. And I call this my Antarctica fun facts slide. So the map here shows what, if I can get this mouse working, the map here shows what our planet looks like basically from the bottom up. Of course, this is Antarctica here in the center, sitting on the South Pole. And you can see how the continent is oriented in relation to some of the other continents. So this here is the tip of South America poking down. This is Africa and Madagascar up here on the upper right. And then of course, we've got Australia. I've lost my mouse. There's Australia and New Zealand. So a lot of times when you see maps of Antarctica, it has this orientation with the peninsula kind of sticking up into the left. And this is because we need a frame of reference to talk about directions. Otherwise, every way is north and it gets a little confusing. Okay, so I'll explain that more in just a minute. Antarctica is a pretty good chunk of real estate. It is the 5th largest landmass on the planet. Maybe to put that in some more useful context, that's about 1.5 times the size of the contiguous United States. It has been described as the coldest, windiest, driest, highest, quietest, most remote, and least understood continent on planet Earth. And it definitely fits the bill on every one of those. Antarctica is the world's largest desert. It is a polar desert, but it is a desert nonetheless. There are parts of Antarctica, like the dry valleys, that have not received any precipitation for millions of years. And probably not too surprising, it's cold. The world record low temperature was recorded in Antarctica at a brisk negative 129 degrees Fahrenheit, below zero, of course. It's also about 99.6% covered by snow and ice. So if you are a geologist or even other types of scientists trying to get down there and look at things, this could be kind of a challenging place to work. So this is what most of Antarctica looks like, okay? This is yours truly standing somewhere out in the middle of East Antarctica. A lot of Antarctica is just flat white, right? On a cloudy day, sometimes you can't tell where the sky ends and the ground begins. And even if we sort of zoom out and look at it from a broader perspective, the image here on the right is a satellite photo. Again, you're not seeing a whole lot of notable features jumping out here. Probably the most notable is this mountain range that runs right through the middle of the continent, which is known as the Transantarctic Mountains. It roughly cuts the continent in half. And I've labeled East and West Antarctica. So when you're on either side of the Transantarctics, that's how we kind of do directions. So grid north, again, is always with this orientation, peninsula pointing up and to the left. So if you hear me talking about like East and West Antarctica today, that's how we do that. So again, not a ton of features poking out here. It doesn't look all that exciting. But if we strip that ice layer off, things start looking a little more interesting. Okay. So what this map is showing is the subglacial bedrock topography beneath the whole continent. The warmer colors are higher topography, the cooler colors are lower. So you can see that there's some very notable high topography regions, including the Transantarctic Mountains that I just mentioned right through here. We also have this area in East Antarctica called the Gamburtsev Mountains. It is a completely subglacial mountain range. They're buried under about 3.5 kilometers of ice, big as the Alps, but you can't see them at all. Really interesting. And we have like this area here called the Ellsworth-Whitmore Mountains. It's kind of a connection with the Transantarctics. Low topography areas, just for examples, we have this area here known as the West Antarctic Rift System that sits below sea level. We also have these two large basins called the Wilkes and Aurora subglacial basins that I'll be talking about a little bit more later. So if you want to get at what is going on in Antarctica, what's causing these different structures and kind of what's helping the processes, including glaciation of the continent, we need a kind of a useful way to get past the ice sheet. And this is where remote imaging methods like seismology can be really useful. So a lot of what my work focuses on is basically deploying seismic stations across the continent. And we use those seismic stations to record signals from earthquakes happening all around the globe. Anything bigger than probably about a 4.5, I can get you. The data might not be quite as good as a bigger one, but we can still see it. So the animation here, it'll start over again in just a second, basically illustrates an earthquake right there at the top of the planet. These lines that are radiating out, the green and the red lines, are meant to represent seismic waves propagating through the interior of the Earth and sampling different structure. Some of that energy is kind of illustrated in the cartoon over here on the right. It will come up beneath Antarctica, up through that ice layer, and eventually get recorded at our stations on the surface. So we can then model those signals with different techniques to try to learn about the subsurface structure. So before I kind of get into the more sciencey part of this presentation, I thought I'd talk a little bit about what it's like to go to and work in Antarctica. I get a lot of questions about this, and I'm totally happy to take, if you want more detail. Right back. So to start with, we got to get there. Okay. The trip to Antarctica is not a short one. I live pretty close to Birmingham, Alabama, so this map here kind of illustrates one potential route I might take to get down there. That leg from LA down to the southern hemisphere is quite a doozy. It's about a 19, 20-hour flight. Usually down to Christchurch, we're taking a commercial flight, whatever airline we book with. But then to get from New Zealand down to Antarctica, we are on some type of military aircraft. Probably one of these two that you see over here on the right. The top picture is what's called a C-17. You can see it's a jet. The bottom picture is a prop plane called an LC-130 Hercules. If you have your choice, opt for the C-17. Okay. The flight on the C-17 from New Zealand to McMurdo is about 4 hours. The LC-130, it's 8. I could get out and run faster. And I have a bad knee. But, you know, one way or the other, you're sitting in a jump seat, your head is on fire in your rear end, and there's no insulation on the inside of the plane. It's super, super loud. Quite these. Once we get down to Antarctica, we need to kind of get our equipment ready. And so these pictures here on the right illustrate some of the equipment that we're going to take into. Oh, these big orange boxes that you see behind me contain most of the guts of our stations, if you will. So all the batteries, electronics, and so on and so forth. You can kind of see down into one of the boxes a little better here in the bottom image. This big orange rectangle that you see is our data acquisition system. It's basically recording the data for us onto it. These packages are kind of shiny black things that you can see right there. Those are lithium batteries that help power our station. I just realized the microphone has been disappearing on me. Sorry. Let me try to fix that. They power the station through the winter months when it's dark 24 hours a day. There's a power module, this little clear box right there that can switch between the batteries and solar panels. So when the sun is up, we can use solar power. There's some other odds and ends in there, including a heating pad to try to keep the box a little warmer than ambient temperature. Fully loaded, one of these boxes weighs about 600 pounds. We then load that box onto some type of transport to get us from whatever base we're working at out into the location of interest where we want to put our site. Most of the time we're using the Twin Otter airplanes. These are very small. I could probably fit at least 4 or 6 of them in this room. Okay. We can get about 2 stations worth of equipment on one plane. It's very, very cozy. Otherwise, we use the helicopters. The helicopters are a lot of fun. The problem is these boxes don't fit inside. So if we're going to do this, we got to sling load the box in a net and carry it underneath the helicopter. Landing that is tricky. Okay. We've dropped I didn't drop this, somebody dropped it. It happens, right? So we get to our site and we start digging holes in the snow. I've gotten really good at digging big holes in the snow. In one of those big holes, we put our big orange box of electronics. Notice how I'm not in the photo because I'm taking it. Pays to be the boss, okay? So I don't have to carry a 600-pound box. But that goes in one hole. Our seismometer, which is the orange dome in the middle picture there, and that is me. That's the actual instrument recording the earthquakes. So we hook all this together. And then this picture on the lower left, closest to me, is one of the solar panels. Okay. So in the far picture on the right, you can kind of see the whole system set up. Here in the background, in this case, we had 2 solar panels providing power, at least in the summer when the sun is up. Coming forward, that's me taking notes, working hard. That's one of my tech guys, Paul, just kind of testing everything inside the box, making sure everything's talking to each other. And then coming here into the foreground, the seismometer is under that little foam hat. You can just see on the edge of the picture here, there's kind of an orange lip there. When everything is set up and ready, we put this big orange dome over the seismometer that you can see the top of here in the picture on the left. And then we kind of backfill in everything with snow. We stick in these bamboo poles that you see and we leave, okay? We do not have the bandwidth to send data back real time. So usually we have to go back at least every year, if not every other year, to physically retrieve this data. The reason everything is bright orange is so you can find it again. That's what the poles are for too, right? So you know it's going to be a really good day when you land and you can see orange and all the poles are sticking out of the ground pretty high. If you can't see any orange and the poles are this far out of the ground, you're like, oh my God, we're going to be here forever. Because then you got to dig all this up, right? So it depends on, how the weather's been, how much it's been blowing, that sort of thing. So we come back, we get our data, we do any repairs that might be needed, we collect our data, and then we leave again. And these can run all year round on their own. Usually the stations are left in anywhere from 2 to 3 years if it's a temporary deployment, but there are permanent stations as well. So the map here on the right, there are a couple of stations missing from this map that are operated by other countries, but it gives a pretty decent summary. Every purple triangle on that map is a seismic station that we installed with a method very similar to what I got up here. I ran the network right down here. You'll see pictures of that a little more specifically later, but I have helped install probably at least a third of these stations, and some of them are still in the field and some of them. So what are we doing with the data? Okay. It takes a lot of time, a lot of investment to get this data. What is it useful for? So for the rest of the talk, I'm going to highlight 3 example projects to kind of give you a taste of the different things we can do with the seismic data and why it might be important. So we're going to start shallow. We're going to start with a project looking at crustal structure, which is important for understanding the tectonic origins of different parts of Antarctica. Then I'll move into a little deeper investigation looking at mantle structure and how solid Earth structure influences the ice sheet or the cryosphere. And then I'll wrap it up with a project I'm actually doing with the folks here at ASU, looking at very deep structure that down near the core mantle boundary. So again, starting project 1, starting shallow. This is a project that focused on the Transantarctic Mountains. Just as a reminder, that's that mountain range over here that's basically splitting the continent in half. The Transantarctics, which I tend to refer to as the TAMs, so if you hear me say that, that's what it is, are again, this very large scale mountain range that separates the continent into east and west. It's about a 4,000 kilometer long mountain range with elevations up to 4,500 meters, so they're pretty sizable. And they think uplift began somewhere around 55 million years ago. They may have actually served as a nucleation point for where the continental ice sheet started to grow from and then spread out from there. What's really odd, though, is this mountain range doesn't show any real evidence for a compressional origin, right? Okay, I realize not everybody in the room is a geologist, but most mountain ranges form through 2 things, hitting one another and pushing all that material up into the air. But we don't see any evidence for the kinds of structures we would expect if that was the origin for the Transantarctics. As you can see in the picture here on the bottom, they have very flat rock layers, right? So something else had to happen, a non-collisional origin had to occur in order to create this mountain range that runs down the middle of the continent. And there's been a lot of ideas about what that might be. So I apologize, this is a little grainy. I didn't realize I was going to give a presentation on a movie screen, but it kind of highlights some of the different ideas about what might have caused the uplift of the TAMs. So the upper panel here is a model that came out by Sturt and Tenbrink in 1989. The hashed areas here show both East and West Antarctica. You guys can tell that apart now. Probably the most critical thing here is this box I've highlighted that says thermal and end load. Okay. The idea behind this model is that you have hotter than normal mantle beneath West Antarctica that's sort of pushing up on the edge of East Antarctica from below and basically pushing those mountains up into the air. So it's a primarily thermal driven model. The upper right panel is from a different study by Studinger et al. 2004 based on gravity data. The top panel with the gray shading just shows a profile across the Transantarctics and into East Antarctica. You can see how the elevation changes. But what's a little more informative here is the bottom panel with the dashed line. This is their model of the crustal structure beneath the mountain range and into East Antarctica. And you can see this crustal root, or this area of very thick crust, which they suggest provides buoyancy to help hold up the mountain range. This bottom picture here is kind of a similar model by Bialis et al. Again, building on this crustal root idea, they took it a bit further and said, well, maybe we started with this area of very thick crust, very kind of an over-thickened plateau that then was pulled apart over time. And then the thick crust we're seeing beneath the Transantarctics is kind of one side of the system, which means there should be another block somewhere else. And then the last one is what I call the everything in the kitchen sink model by Lawrence et al. 2006. Kind of what I said, everything got thrown into this. So there's a crustal root in here that you can see by the brown shading. The red color here indicates that thermal load, so this hotter than normal mantle pushing things up from below. There's a few other odds and ends in there as well. So we'd really like to know what is the crustal structure beneath the Transantarctic mountains, because it might allow us to get a better sense of which of these models is maybe the most viable for the origin of the mountain range. And again, this has a lot of implications for understanding how Antarctica came together as a continent and ultimately led to the large-scale glaciation that we have today. So in seismology, I'll keep this light, I promise. One way that's very commonly used to map crustal structures is to use what's called a receiver function. Basically, when you have a boundary in the subsurface, like the cartoon up here, you can have one type of wave convert to the other. So a P wave can change to an S wave or vice versa. Okay? We can isolate those converted waves using an approach kind of illustrated in the cartoon here in the middle. This is two different components of a seismic wave. The motion in the vertical direction, the one in the horizontal direction. And we basically deconvolve or sort of remove one component from the other. It cancels out the parts that are in common, and then we're left with these converted signals that we're interested in that we can then model to find these discontinuities that we're looking for. Okay. So again, these converted signals can be super useful if we're trying to map out, say, the moho, right, the base of the crust, and get at crustal structure. The problem is that bloody ice sheet. Okay, so the top cartoon here illustrates the case with no ice. Very, very simple Earth model. I have a 30-kilometer thick crust underlain by a mantle half space, like this, about as simple as it gets. And then over here on the right, I have synthetic receiver functions, both what are called P-wave receiver functions and S-wave receiver functions. The only difference is a P-wave receiver function is looking at P to S conversions. S-waves are S to P conversions, right? And again, if you need a little guidance, you can look at the cartoon up here on the left. So in this case, the first big peak that we see is the direct phase, whether that's P or S. And then sometime later, we have another bump showing up here, and that's the converted signal, either the P to S or S to P conversion, in this case from the moho, right? The base of the crust. So we could model that and figure out how thick our crust is. If you don't have anything else going on here, you can see the amplitude in the P-wave receiver functions a little more pronounced, so probably a little easier to work with. Right? However, if we come down here to the bottom cartoon, same Earth model, right? 30-kilometer thick crust, mantle half space. All I've done is thrown a 2-kilometer thick ice layer on the top, which is very within the constraints of how thick ice is in Antarctica. Most places it's probably thicker. And if you look at this, these are now the synthetic receiver functions. And at least the P-wave receiver function has gone wackadoo, right? What's happening here is when you have a slow layer at the surface, like an ice layer, that energy gets in there and just reverberates or bounces around like crazy. So it's basically clobbering the signal, that moho P to S signal that we're really interested in. It's kind of lost back here in all this other junk. Again, all these reverberations within the ice layer. However, this is where your S-wave receiver functions can be really useful because there's a better timing separation between the signal we're actually wanting to see and those reverberations. So again, we've got, excuse me, kind of this big peak out in front here. In this case, this is the direct S wave kind of squashed together with the conversion from the bottom of the ice. But this moho bump, that's the thing we're really interested in. So we can use this to model the crust. So these are results from two different studies. The one on the left is from the central part of the Transantarctic Mountains that I did back in 2009. The one on the right was primarily spearheaded by Lindsay Kenyon in the northern Transantarctics. The dots with the error bars indicate our measurements of crustal thickness, again, based on these S-wave receiver functions. And then you can also see the profiles in the top panel, just how does the elevation change, and the blue shading is the ice thickness. So if we kind of look at these together, both beneath the central and the northern Transantarctics, yes, there's some variability and uncertainty, but within error, our estimates are pretty much the same, right? And while there's maybe a hint of a local route beneath the northern Transantarctic Mountains, this isn't super obvious, and it's not continuous along the length of the mountain range. We're not seeing it in the central Transantarctics, for example. So this constraint on the crustal structure kind of indicates these crustal root models don't really work because you don't have a consistent route beneath the mountain range. From that same study or the same data set, some of my other students looked at what's called tomography. I'll talk about that a little more later, but they also investigated this same question. This image here on the left, basically what you need to take away from this, if you see blue colors, that means your seismic waves are traveling fast, so the material is old and cold. If it's red, they're traveling slowly, so it's young and hot, okay? So this example here shows how these materials or how these velocities are changing in our study area. What's really interesting here is that we see the most red, in other words, the hottest or the slowest material, coincidental with the areas where we have the highest elevations in the TAMS, such as the Deep Freeze Range and the Royal Society Range. In the middle, where those red values or those red colors are sort of lighter and concentrated further offshore, we have lower elevations in the mountain range, like in the Prince Albert Mountains, which is really interesting, right? So there's this really interesting correlation between elevation and seismic velocity, i.e., where you have old or cold or young and hot material. It's kind of putting this all together. These results, along with our crustal results that I just showed you, are probably most consistent with this type of uplift model, again, from Stern and Tenbrink, where the dominant force leading to the uplift of the TAMS is this thermal load pushing up on East Antarctica from below. Again, this has a lot of implications for understanding how did this mountain range form, how did the tectonic history of the continent, how did this continent come together, and ultimately, how is that affecting things we're seeing today? We're going to dive a little deeper now, okay? So we're going to focus on the upper mantle. And in this case, we're kind of going to look at the importance of Earth structure from a slightly different perspective in that how it affects the ice sheet. Okay? So how an ice sheet behaves really depends on what the underlying Earth structure is. How thick is the lithosphere? What's the viscosity and temperature of the mantle? All of these things can either act to either hinder or enhance ice flow. The two cartoons here illustrate both situations. So for example, the image here on the left is a case where we have very rapid uplift of the underlying bedrock after losing some ice. And you can see this red line here labeled ABC. This is what's called the grounding line. It's where the ice sheet is in contact with the underlying rock. Okay? So because we've had this very rapid uplift, it's basically shifted that grounding line closer to the coast from A to C. It's put more contact between the ice sheet and the rock, and that's actually going to slow that ice sheet down. So in this case, the solid Earth structure is hindering ice flow. It's preventing further ice flow. The other cartoon on the right, in this case, we have hot convecting upper mantle. It's pumping out a lot of heat. So your geothermal heat flux, or your GHF, is going to be much higher. You're putting a lot of heat into the lithosphere and the base of the ice sheet from below. It's going to promote more melting. Stuff's going to slide easier, and you're going to have more of an effect for ice loss. Okay? So there's a lot of questions about what is the solid Earth structure beneath East Antarctica in particular, and how does that affect the East Antarctic ice sheet? And the reason people are interested in this is because East Antarctica holds an ice volume equivalent to 52 meters of sea level rise. It's a lot, okay? And recent studies have shown that about 32% of cumulative sea level contributions, at least since 1980, have come from what's called the Wilkes Land sector of East Antarctica. So this is a map very similar to what I showed you before. Again, the subglacial bedrock topography. If you just need to orient here, we're looking at this shaded region on the inset map, okay? And I pointed out these low topography areas, the Wilkes subglacial basin and the Aurora subglacial basin, kind of a little earlier in the talk. Okay? It's been suggested that both of these basins could play a pretty significant role in affecting the stability of the East Antarctic ice sheet. And again, this quadrant of East Antarctica is what we call Wilkes Land. But we don't have a lot of constraints on this. We don't really understand the origins of these basins. How did they form, right? What's the tectonic history behind them? We don't know how thick the lithosphere is. We don't know what the underlying mantle structure is. These things are not very well constrained. And in order to understand the ice sheet, we kind of got to know what those details are. So the goal of this study was to develop a new seismic velocity model, particularly S-wave velocity model, to try to better understand the structure in Wilkes Land and in these basins. And again, then to try to understand better how this impacts the East Antarctic ice sheet. So again, briefly talking about method, this project is doing what's called full waveform ambient noise tomography. Realize that's kind of a mouthful. So let's break that down a little bit. Ambient noise or ambient seismic noise is the noise that's around you all the time. It's constant, right? It's just sort of the natural wave field that if you put a seismometer in this room, you're going to pick up, okay? Most of that noise is due to ocean waves beating on the continents. There's other sources too, but a lot of it comes from that. So some very clever person, probably smarter than me, figured out that if you take the noise waveform, the seismic signal, between two stations, and you cross-correlate those stations, cross-correlate the noise of those two stations, you can actually figure out or extract the signal they have in common. So now your noise has become data. And that signal depends on the subsurface structure between those two stations. So the maps here on the lower right, each one of these colored lines extends between a pair of seismic stations in Antarctica. The color of the line, as it says on the bottom here, is the number of months of overlapping data between those two particular sites. And you'll notice that these are split out by frequency. Okay? So we filter these data into different frequency bands because they're what's called the dispersive. Higher frequency signals are sensitive to shallower structure, and lower frequency signals are sensitive to deeper structure. So we can map how the subsurface structure varies from top to bottom. We also use synthetic waveforms to better constrain our results. Basically what we do is we make up a model, okay? And we use that model to predict what the signal should look like. We compare the synthetics and the actual observed data and go, they don't match very well. We update the model, we do it again. So it's an iterative process to minimize the difference between the synthetic and the observed data. So this has been a really interesting project, and we've discovered all kinds of cool things with this. The map on the upper right and then the corresponding cross section, which goes down that black line there, are from our results. The Roman numerals are a bunch of different anomalies that we've identified. I don't have time today to go into all of these, so I'm going to just focus on a couple of things. The first thing I'd like to point out is sort of this comparison between these top two maps. The map on the upper left is from a pretty recent study by Lloyd et al. And this is what most tomographic models of Antarctica, at least in this part of Antarctica, look like. Kind of this consistent, fairly uniform blue color associated with fast seismic velocities, not a lot of variability. And again, if you remember what I said a moment ago, again, fast velocities is old and cold, right? So a lot of people have seen this and said, oh, it's all just one big craton. But if you look at our model, yes, we certainly have areas that are blue and fast and probably associated with craton, But we're seeing a heck of a lot more variability here, particularly beneath those subglacial basins, the Wilkes and the Aurora Basin. So again, in the interest of time, I'm going to focus on the Aurora Basin, which is anomaly 5 right here. Again, map view and cross section down here. Okay. And we wanted to really get at what is going on in the Aurora Basin, because no other tomographic model that has been created before has ever ID'd this mantle structure. So I ran a whole slew of synthetic tests to try to figure out what this is and whether it's real structure, right? You know, is it something like an artifact? So you're going to see a couple of images here. In each one of these, the topmost panel is a cross section through our model, right? We're going to focus on anomaly 5. The middle panel is an input model. It's a synthetic, something I made up. And then the bottom panel is how that synthetic is recovered using the same data we use for our actual model, right? So the upshot here is you want to compare the top panel and the bottom panel. So for starters, I tried to just put in one continuous fast layer of thick craton across all of East Antarctica to see if by some chance I could get back the structure we see. They don't match, right? So again, this kind of uniform fast craton doesn't really work. I tried putting an anomaly offshore. Prior work has shown that there's mid-ocean spreading centers offshore Antarctica. Like, well, okay, maybe you have slow velocities offshore. Somehow that signal is kind of smearing into our model space and it's causing an artifact. You get a little hint of some red interference, but nothing that looks like the anomaly we're actually seeing. So this offshore influence doesn't really seem to explain this either. I also stuck a sediment layer in the basin. A lot of people have argued how thick the sediments are in the Aurora Basin. But same deal, I wanted to see if I introduce this, could this again smear downward into our model space, explain that anomaly. Again, a little bit of red, but nothing as pronounced as what we're seeing. So these and other tests I've run have really illustrated that this is not an artifact in the model. It appears to be real structure. So that sort of begs the question of what is this? So these again is model input and output synthetic, and this is our best match synthetic, right? This is about the best I could do to match the observed structure. So in the Aurora Basin, the kind of right side of this, our best fit model includes a relatively thin, about 100 kilometer thick lithospheric lid, that's the blue part, underlain by a fairly pronounced slow seismic anomaly that extends to about 250, 300 kilometers depth. Our estimates of the lithospheric lid, how thick is the lithosphere, agree relatively well with prior geophysical studies. But that mantle anomaly, that slow blob that we're seeing, is really new to our model. It's newly recognized, and we need an explanation for what it is. So our best interpretation for this is we think it's some kind of thermal perturbation to the upper mantle. And there's some other lines of evidence we've pulled in to try to make a case for this interpretation. For example, if you look at estimates of geothermal heat flux, GHF, not based on seismic data, right? If you go to other kinds of data like magnetic data, for example, a lot of those models argue for high heat flux in the Aurora Basin. This map is an example of that. This is a study that was done by Artemeva in 2022. And this pink area right in here is the Aurora Basin. Again, that pink color illustrates high geothermal heat flux in that region. So some kind of input from the underlying Earth. This other image here that I took from Frederick 2015, the blue and the red symbols on this map indicate the location of subglacial lakes, so basically melt puddles, if you will, at the base of the ice sheet. And the Aurora Basin actually contains the greatest concentration of subglacial lakes in the whole continent, right? So it's been argued that there has to be some kind of heat input in order for that to happen. In one of those lakes, particularly Lake Vostok, which is the LV right there, they've actually found thermophilic, heat-loving bacteria in the water, which is quite interesting. And the very high elevations across East Antarctica that we see a lot of people have argued require some kind of like support or push dynamic compensation from the mantle, pushing it up from below. So all these other lines of evidence kind of fit with the idea of having a thermally perturbed upper mantle. Why? Okay. So our best interpretation is illustrated in the cartoon here at the top. It's been suggested by other studies that some kind of accelerated flow in the mantle could lead to the development of mantle plumes or upwellings in the mantle beneath the Aurora Basin. And these may have actually activated rifts that either formed originally or were even reactivated older structures in the basin. So the cartoon, as you see here, we've got some kind of upwelling from the mantle, kind of eating away at the mantle lithosphere from below. You get that thinning of the lithosphere, hot material at depth in the mantle, and then it causes extension in the overlying area. And this really works with our seismic model here, with, again, thin lithosphere, deep-seated slow anomaly, as well as all those other models or other studies that I just showed you that advocate for geothermal activity in this region. So who cares, right? I think it's cool just because, but there's bigger scale implications for this. Again, we're interested in what the ice sheet is doing. Is this thing going to melt and dump all this water into the oceans, right? Is Florida going to drown? Okay. So the fact that this model that we've come up with advocates for thin lithosphere, thermally perturbed upper mantle, particularly beneath the Aurora Basin that I showed you today, is consistent with, again, higher geothermal heat flux and probably decreased mantle viscosity, right? It's more runny. Both of these have pretty dramatic implications for how the ice sheet is going to behave, because you're going to increase melt rates at the base of the ice sheet with higher heat flux, and the difference in viscosity is going to depend on how that thing responds as you load it or unload it, okay? So it could be that the structure that we've imaged might help to explain why the Wilkesland sector of East Antarctica is really dominantly contributing to sea level rise, at least from East Antarctica. And that's what's illustrated in the picture here from Renaud et al. 2019. These big circles indicate contributions to sea level rise and ice mass loss. So the takeaway from this is if someone's gonna work on modeling the ice sheet in the future, which is a big concern, this kind of tectonic structure probably needs to be taken into account. The last study I'm going to highlight today, again, we're moving deeper, so we're going to go all the way down to the core mantle boundary now. And again, this is work that I'm doing with folks here at ASU. So the core mantle boundary is associated with all kinds of weird phenomena. It has the biggest change in physical properties on the entire planet. So as you go from mantle to core, the change in physical properties is more dramatic than that of you going from air to rock, okay? So home to a lot of weird stuff. We don't really completely understand what's going on down there. But one of the features that have been recognized is what's called a ULVZ, which stands for an ultra low velocity zone. Okay? ULVZs, it depends on the study you look at, but they're sort of 5 to 50 kilometers thick, so sort of tens of kilometers thick, sitting right above the core mantle boundary, very lower part of the mantle. The reason they're called ultra low velocity zones is because when a seismic wave moves through them, they go a lot slower. So you're talking about very strongly reduced P&S wave velocities. Some studies have also suggested they're associated with an increase in density. Okay? The maps up here, the colors are a little washed out, but hopefully you can still see them okay. The areas highlighted in gold are places where prior studies have found evidence for ULVZs. Those outlined in blue don't show evidence for ULVZs, and those outlined in red or pink or whatever that color is are like, maybe there's ULVZ there, but we're not quite sure. Okay. The big pink blobs that you see are what are called large low velocity provinces, or LLVPs. There's 2 of them on their planet. These are much bigger scale features than the ULVZs. There's one beneath Africa and there's one beneath the Pacific. It may be that ULVZs are found in somewhat greater concentration near these larger scale features, but as you can see from the maps here, they're kind of all over the place. Okay. So there's a lot of questions here about, well, what is this? What is a ULVZ? Where do they come from? Is this part of Earth's larger scale convection cycle, or is this like something unique to the deep mantle? What's going on here? Okay. And I'll also point out with the map on the right, same map, just plotted with a different viewpoint, there are not very many studies in the Southern Hemisphere. Okay. So, geodynamic models have suggested that subducted oceanic materials, subducted crust, subducted oceanic sediments, could be carried down into the deep mantle in subduction systems. So the right side of the cartoon here, the blue thing coming down that says subducting slab, is basically pulling that oceanic material down and introducing it into the deep mantle. That material could move or advect along the core mantle boundary, and eventually it meets one of those LLVPs where it might get swept up into sort of a big upwelling and kind of carried back up and recycled into the mantle. So the question has been put forth of, could ULVZs be associated with these subducted materials, right? Being introduced in the lower mantle and moving across. So our study wanted to investigate the lower mantle beneath the Southern Hemisphere, because as I showed you in the previous slide, not much has been done there. And this is an interesting area to look at this problem because Antarctica is not immediately near any of these LLVP upwelling areas. And it's also not really nearby any areas of recent or current subduction. So you're kind of in that in-between, kind of the middle of that cartoon up there. That provides a neat place to kind of target this. To do this, we're using what are called core reflected phases, seismic waves that bounce off the core mantle boundary. Particularly for this talk, I'm going to focus on what's called a PCP wave. So the image here, the red star is the earthquake being recorded, being recorded at a station over here, the black triangle. This is the direct P wave. The other is the PCP wave bouncing off the outer core. If we zoom in onto this box, that's what this image here is supposed to represent. And you'll notice here we have that kind of pinky tan colored layer. That's our ULVZ, right, our ultra low velocity zone, sitting just above the core mantle boundary. So a regular PCP wave is the red arrow here. It comes down, hits the core, bounces off. But we can also get other signals being created if a ULVZ is present. You can get reflections off the top of the ULVZ, like the blue arrow here, and we call that a precursor because it comes in sooner. Or you can have energy bouncing around inside the ULVZ. It's going to take a little longer to get to our seismic station, so we call it a postcursor. It shows up a little bit later. But you're only going to get these pre and post cursors generated if you have this layer down there. So what our goal for the study is to look at these types of waves, these PCP waves, that sample certain portions of the core mantle boundary, see if we see evidence for these pre and or post cursor signals, and ultimately use this to map out the structure on the lowermost mantle. So the image here on the lower right illustrates what one of these might look like. The black line is what's called a PCP stack. We basically select some area on the core mantle boundary, and all the earthquake signals sampling that spot are added together and averaged. So that's the data that we get. And then the green and the red lines are synthetic data. The green dashed line is a model that does not contain a ULVZ, and the red one does. So this bump here that I've labeled ULVZ precursor, in order to fit that signal that's coming in before the PCP wave, we have to introduce a low velocity layer. Okay? Specifically in this example, our best fit was a 20-kilometer thick ULVZ with 30 and 11% reductions in the P&S wave velocity respectively. Sorry, I did that backwards, S&P wave growth, and then a bit of an increase in density. So we can do this at all different locations around the lowermost mantle and try to map out how ULVZs vary. So this is a compilation map that I pulled together for a number of different studies, some of which I did, some of which my students have done. Basically, anything that's plotted over there as a red dot are data that have met a bunch of criteria, and we think show really strong, robust evidence that yes, there is a ULVZ here. The ones that are plotted as yellow dots are not quite as certain. They didn't meet quite all of our criteria, but we're like, yeah, there's probably something there, but we're not 100% sure. The background is one of these seismic tomography models. Again, blue is fast, red is slow. So blue is kind of presumably cooler temperatures, red is a little warmer temperatures. And these purple dashed lines here, those are the outlines of those real big scale LLVPs that I mentioned. So what we're seeing here with the different studies that we've done is we kind of find ULVZ evidence sort of all over the place, right? It's kind of widespread throughout the Southern Hemisphere, but it's not uniform, right? Some places it's thicker, some places it's thinner. The velocity characteristics might change. And so we need to come up with a model that can explain that. How do you get this widespread but variable structure ULVZ? You'll notice that a lot of our sample points are kind of sitting on that blue background, right? In other words, they're in the fast or presumably cooler parts of the lowermost mantle. So there have been suggestions that ULVZs are purely associated with some kind of temperature anomaly. But if that were the case, you wouldn't see them probably in this fast background. So something with a compositional variation seems to be necessary. Yes. Okay, I will speed up. I'm close. So one possibility is that we had a layer of what they call it, a basal melt layer that originated early in Earth's history. It may have formed at the bottom of the mantle, segregated over time, and left this kind of mushy layer behind. Could be the source of ULVZs. The problem with this idea, though, is this thing has been sitting around for billions of years. How do you keep it from migrating and moving and getting recycled back into the rest of the mantle? The other cartoon is a different idea. This is an iron enrichment from the outer core. Basically, we're pumping iron into the lower mantle, makes denser, slower material. The problem is this is a temperature and pressure dependent relationship. So you would think if this was a good model, you would see some trends in where you see variability in those characteristics versus, say, the thickness of a ULVZ, which we don't. And again, we're not really sure if these types of reactions will actually produce enough material to create ULVZs. So again, let's come back to that subduction idea. Could that work? Okay. So this is a model I'm going to play for you that Mingming Li here at ASU put together to assess if you had subducted materials, could they get to our study area in Antarctica? Okay. So when I start this, it's going to run from 460 million years ago to present day. You're going to see some colors starting to show up. Basically, these are the number of tracers. You can think about it as the amount of subducted material that's moving from the near surface down into the lower 50 kilometers of the mantle. I'll go ahead and get this. Oh, shoot. All right, are you not cooperating with me? This is really hard to do with this mouse. There we go. And the arrows show the direction that stuff is moving. So you can see as this thing moves through time, we start getting more and more subducted material introduced into the deep mantle. It's going to shift around. You're going to get piles of it, like that blue blob that just showed up, where you have more subducted materials accumulating, and areas where it's lighter in color and you have less subducted materials, right? So this kind of mimics what we're seeing with the seismic results. You have this fairly widespread material with variable structure distributed throughout the lowermost mantle beneath Antarctica and the Southern Hemisphere. So let's let it, it's probably fine. So this is really significant because it's starting to tell us that maybe these features are part of this larger scale convective processes that shape the whole bloody planet, right? So it's got a lot of neat implications. So I know I'm getting low on time, so I'll wrap this up. There's a lot of time and effort that's gone into putting in seismic stations in Antarctica. The data that we've acquired has led to all kinds of new investigations and new discoveries from the crust all the way to the core, but there's all kinds of things still to be learned. So there's a lot of new room for contributions, both in the field and in the computer lab. So I will end this with some obligatory penguin photos. And thank you.
All right. Thank you, Sam.
I'm sorry if I went too long.
Super cool. You just have too much to say.
Yeah.
All right. So we like to invite students to ask questions first before we get to the non-students. Well, we're all students, right?
This thing keeps sliding on me.
Aaron?
I'd be Claire. I was going to ask for the rock layers that you showed in the TAMs. Do those have corresponding, like, do you know what the origin of those units are? And do they have any corresponding units in other parts of Gondwana, or were they kind of post that?
So most of the base of the Transantarctics is metamorphic and granitic, but the majority of them is sedimentary. And a lot of them were associated with kind of a shallow marine environment that then got uplifted. Are they associated with rocks elsewhere? Some people have argued there's like correlations in Australia that might match up. There's also ideas that maybe they're somewhere in West Antarctica, but again, everything's buried under snow and ice. So it's kind of a difficult thing to answer. Possibly. We don't completely know.
And then I had a second question of, on the mountains that are still sticking up above the ice, is there kind of like a record of fluvial incision on kind of the geomorphic side, or has it been completely overprinted?
Yeah, so actually part of the uplift models include an erosional component. Some of it may be fluvial, some of it's also associated with ice sheet erosion, because as you remove that material, it's going to respond and everything's going to bounce up. So most of the uplift models, at least on some level, do include that component to explain part of the uplift. The question is how much, right? And there's disagreements about that. Some people think there's been a lot, some people think there's been a little. Okay. Pressure.
Yeah. Quick question for your lithosphere model for project number 2. Are you planning to do a joint gravity inversion?
Maybe. The only gravity data we've got is satellite gravity data, and I haven't done a lot with that. I think it'd be a really unique project. Part of it is getting the right frequency of seismic data that works with the constraints of the gravity. Usually gravity is, my understanding, is more shallow structure, and we're kind of focusing deeper, but they could complement each other. It's certainly something to think about. I just got to find the right collaborator. So if anybody's looking for a project.
One last burning question. Yes?
You told like beneath Antarctica, like there are like thermal anomalies and there might be a plume. So is there, like, from the seismic data, can you detect like if there is a connection of that like plume like things with the deeper mantle structure, or like whether they're coming from the deep mantle or from the shallower part?
So with the resolution we've got, we can only see down to about 300 kilometers right now. I would need broader scale seismic data to answer that, which is a little bit of a stick. I'm trying really hard to get more seismic stations in Antarctica. I don't know where he went. I had a discussion about heard my French, logistics in Antarctica are a shit show right now because of COVID and just other priorities. So getting back out there has proved to be very difficult. I'm hoping someday, yes, we will be able to answer that. So.
I knew you were going to swear. Okay.
My parents were both sailors.
Your parents were sailors. So
sorry.
I'm going to leave that alone. So you can come down and ask Sam questions, and let's thank Dr. Sam Hansen again for a great talk.
Thank you. Turn this off.